Good afternoon, everybody, and welcome to this afternoon's Be Curious family-friendly event, Laser, Security and Space, Terahertz Waves. So my name is Shawnee, and I'm one of the organisers of Be Curious here at the University of Leeds. Each year for Be Curious, we invite you guys to take a peek at what really goes on inside a university. And this year, as you can probably tell, we're coming to you from Be Curious HQ, which is slightly different. We're online, but that means that you can design, make, imagine, do, glue, explore, and so much more, all with us from the comfort of your own home. So we're going to be going live with Be Curious activities right up until the 15th of July. And some of you, if you're very lucky, might have joined us already. But if not, you can head over to our YouTube channel just after this and catch up with some of the activities that we've already been running. Be sure to check out the rest of the programme after this afternoon's event. There's loads of stuff on offer, including family-friendly activities every day at 4 o'clock. And we've even introduced a brand new series of events for grown-ups called Be Curious Lates, and we're running them at 8 o'clock each evening. So back to this afternoon. I know you're all here queued up and really excited to go. We're going to be exploring gigantic, powerful lasers, security, space, how we use these lasers, and learning a little bit about something you might not have heard of before. And this is going to be new to me, so I'm really excited. Terahertz waves. Now, we want to encourage you guys to use the chat to answer questions, ask questions, talk, say hello, and you should be able to see that right now on your right-hand side over there if you're viewing us in YouTube today. If you're not already viewing us in YouTube, we recommend doing that to get the best experience. So what I'd say is hover over your little screen and you should see the option to view in YouTube. If you click that now, it might open a new window, but we should appear and you should see the chat on that side. So we've got some fantastic moderators on board today, Phoebe and Merrin, who are really keen to say hello to you and have a little bit of chat in that chat. So why don't you say hello now and drop them a comment? If you can say hi, tell us where you're tuning in from, who are you watching with? It might be mum, dad, grandma, grandpa, auntie, uncle, baby brothers and sisters, pets, anybody. We would really, really like to know where you're tuning in from and joining us today. So now I think we should get on with this afternoon's activity because we've got some really exciting demonstrations to show you. And I'm really, really pleased today to welcome Thomas and Jack, and we've also got Nick on board from behind the scenes, and they're joining us from our School of Electronic and Electrical Engineering at the University of Leeds. So I'm going to welcome them to the stage now. Hi, Thomas and Jack.
Hello.
I'm going to hand over to you. Have a great time, everybody, and make sure you throw some questions in the chat for them. Okay.
Okay. Yeah, thanks for introducing us, Shawnee, and thank you to all of the moderators behind the scenes as well. I'm Thomas.
And I'm Jack.
And we're both PhD students here at the University of Leeds, working with terahertz radiation, part of the Hyper-Terahertz Consortium, which is a group of researchers split between University of Leeds, University of Lancaster, University College London, and the University of Cambridge. Just off the screen as well, we have our cameraman Nick. Say hi, Nick.
Hello.
And he's here to help with the technical side of things, as well as he's going to keep an eye on the chat as well. So if you've got any questions you'd like to ask us, we're hoping to have a bit of a question time at the end of the session where you can we can try and answer it to the best of our ability. Yeah, so we're here today to talk to you about terahertz spectroscopy. But first, what is terahertz spectroscopy?
So spectroscopy is a way of telling us what an object is made out of. It works by us pointing some light at the object and seeing how that light is changed afterwards. So this happens because some of the light is absorbed by the object. By seeing how that light is changed, we can work out what the object is made of. And that's because every material has its own unique fingerprint. Different materials absorb and transmit different colors of light to varying degrees, meaning that every object acts differently depending on what colors of light are shown on the object. So we can work out what it is.
Okay.
Sorry about that slight technical blip, everybody. We seem to have lost Thomas and Jack. But I think in the meantime, while we wait for them to get back, you guys could drop them some questions in the chat. Tell us what you want to see today. What do you want to find out about the super powerful laser beam? What do you think a super powerful laser beam can do? and I'd like to see some of your responses. And I'll flash them up on the screen if you can tell us that. Also, I can say hello to some people who've already been joining in on the chat. So we've got Anise who's watching from Bradford. Hi Anise, I remember you from some of the other sessions already. And hi, Tessa is joining us from Leeds. Oh, and I think we might have just got Thomas and Jack back after our technical blip. I'm going to add them back in and say, hello guys.
Hello.
Are we back?
Technical difficulties.
Technical difficulties. If you want to get your slides ready for me again, we're just talking in the chat about what we think these powerful laser beams might be able to do.
Okay. What are people's thoughts then? Have any of you heard of terahertz before?
Let's see. I already said terahertz are totally new to me, so I'm going to learn something today.
Yeah, it's quite a I say new science. It's been around for like what 20-ish years, something like that, which in science terms is quite new, but yeah, it's still quite unknown to a lot of the general public.
Okay, so we seem to be back up and running.
Cool.
I'm going to leave you guys to carry on.
Okay. Yeah. So I don't know where we got to. If you want to, come on. Yeah. So what is spectroscopy, Jack?
So spectroscopy, don't know how much you got before. It's a way of telling us what an object's made of. We shine light at it, and the light changes because some of it is absorbed by the object. And this lets us work out what it's made from. Every material acts differently upon being hit by light, so that means that we can work out what it is. So that's useful for loads and loads of different things, such as detecting illegal substances like bombs and drugs in airports when we travel. It can be used medicinally, so we can check that the right amount of medication is in a tablet or fine tumors in a body. We can look for forensic evidence at a crime scene like blood stains. And it has loads of space applications as well. So astronomers can use spectroscopy to find planets millions and millions of light years away, and it can help us tell us what kind of planet it is. Like, is it a big gas giant like Jupiter and Saturn, or is it a small rocky planet like Earth and Mars? And it can even help tell us if that planet is habitable. Okay, so now we know what spectroscopy is, but what is terahertz?
Okay, so terahertz is a range of colors of light in the broad spectrum of all of light. So normally, day to day, you can only see quite a narrow range of it known as the visible region. But there's lots of other range of colors that we can't see, like ultraviolet, X-rays, gamma rays, radio waves, and microwaves. These all have different uses. So for example, X-rays can be used to look at broken bones. Microwaves can cook your dinner, send text messages, and radio waves can send TV signals and, of course, play the radio. The type of light that we work with here at Leeds with hyperterahertz is called terahertz, and it's sort of the part of light in between microwaves and infrared. So
why then do we want to use this terahertz light? What is it that this can do that other types of light can't do?
Okay, so terahertz is non-ionizing, which means it's safe to use for around people. You don't have a chance of damaging your cells like you do with X-rays and gamma rays, for example. As well as this, we can use it to see through plastics and clothing, just like how in the visible colors of light, we can see through glass like windows and things. As well as this, crystals such as drugs, explosives, and glasses all react uniquely in the terahertz region, meaning that we can very easily tell them all apart. As well as this, terahertz is reflected by metallic objects and absorbed by water. It's a vastly underexploited region just because of how difficult it is to make light of this color. But why do we then want to use this for spectroscopy? So it's because of these features, it's perfect for being a security scanner. So we can see through packaging materials like clothing, like plastics, paper, and we can see if the thing inside is good or not, whether it's like an illegal drug or an explosive or something, which brings us on to our demonstration. This is going to take a second while we rotate our camera. Okay. Yeah, would you be able to go to full screen video? Thank you. Okay, we're a little bit tall here. There we go. Yes, so here we have a mock-up of a Terahertz security scanner. And what we need your help at home is to help us identify some mystery boxes of what's inside and whether we should put them in our delivery van that's just off camera. So the way the security camera works, just like how light reacts uniquely with different materials, when we put objects in our security scanner, it's going to play a noise for each different material. So we've got 5 different materials that might be in these boxes. We've got flour, we've got sugar, we've got explosives, we've got illegal drugs, and we've got some painkillers. So first of all, we're going to put these in one by one, so you all at home can have a listen and try and remember what they sound like, and then we're going to put in the mystery boxes. Let's start off then with flour. Let's see how flour sounds like in our security scanner. Okay, I hope you can hear all that at home. Let's try that again. Let's scan it again. And again. And much more for good measure. There we go. Okay. Next up, let's try the sugar. Let's see what that sounds like in our scanner. Okay, what do you reckon that sounds like, Jack?
It's very interesting, isn't it? It sounds a bit like an old arcade game.
Yeah, it does a little bit. Let's try scan it again. Do you all hear that at home? And let's try scanning it once more. Okay, so that's sugar. Let's try next with some painkillers. Oh, wow, that's a very different sound. Sounds a bit like a spaceship or something. Let's try that again. And again. Okay. Next up, let's try and see what illegal drugs sound like in our scanner.
So all the previous stuff we could put in our lorry, but this we can't.
Oh, that one's a lot softer. It sounds a bit like a gong or something.
Yeah, like a muted bell of some sort.
Let's try that again. Very quiet. I hope you can hear that. Let's try one final time. Okay. And finally, let's see what explosives sound like in our scanner.
Be very careful with this.
Yeah, have to be very careful with that one. Oh, much more high-pitched.
Sounds a bit like you've got an answer wrong on a game show.
Yeah, a little bit. Let's try that one more time. Okay. So, now that we've heard all of these sounds, we're now going to start putting our mystery boxes into our scanner. So inside these boxes is going to be either 1 or 2 of the items that we've just played through the scanner. So I want you at home to try and figure out what's in the package and whether we should put it in our delivery van. Let's start off with mystery box number 1. What do you reckon, Jack?
I think I might have it, but I'm not sure. Can you play it again?
Let's try scanning it again. So do you all want to try and put it in the chat what you think it is? We'll come to the answers later. Okay. Let's try that once more. Okay. Let's try our next mixture box. Let's see what this one sounds like. One of those high-pitched ones. Let's try that again. Any ideas at home? Okay. Let's try our next mystery box. Mystery box number 3. See what it sounds like. That one sounds like a mixture of them.
Yeah, there's more than one item in this one, isn't there? I'm gonna have to unscramble the sounds.
Yes. Let's try to play that again. See if we can unscramble it. Let's try that again. One last time. Okay. Hope you're all doing well at home. Let's try our next mystery box. Mystery box number 4. Well,
This box looks more suspicious.
yeah, it definitely looks a lot more suspicious. I would want to put that in my delivery van. Let's try scanning it again. A lot more complicated sound, that one.
Yeah,
A
there's
lot
definitely
going on.
more than one item in this one.
Let's try that again. Okay. Now let's try our final mystery box. This is a very big one. Also looks very suspicious.
Yeah, this looks pretty battered. Must have been through the mail a few times.
Yeah. Let's try playing that again. Yeah, it's definitely a mixture in this one as well. Okay, and let's scan it one more time. Okay, I'll give you all a little bit just to try and figure out what it is. Then we'll move on to the results. So then, Jack,
Yes.
mystery box 1.
Ooh.
What do you reckon was in there?
Well, it was tricky, but I think this one was painkillers.
Painkillers. Let's see what was in mystery box number 1. Was indeed painkillers,
Yes.
which means that we can put that in our delivery van.
Amazing.
Okay, mystery box number 2. One item in this again. What do you reckon's in there?
I think this one. I wasn't sure about this one. It sounded to me like it might be sugar.
Not quite.
Oh no.
Explosives in this. We can't let you put that in the van, Jack.
Oh, I would have been fired on the first day.
So yes.
I hope you're doing better than me at home.
Yes, I hope you did better than Jack at home. Let's try our next one. Mystery box number 3. So this was our first package with a mixture of 2 items in there.
So, I think this one, it sounded like painkillers again. I think I got painkillers down. And then the other item, was it illegal drugs?
Let's see. So you're definitely right with the first bit.
Yeah.
We've got painkillers in there. We also have illegal drugs.
Oh,
Correct. Well done. So yes, that should not go in our delivery van. Mystery box number 4. This one's another mixture of 2. What do you reckon?
I think this one sounded like, I think there's some flour
Mm-hmm.
and maybe some sugar. I think maybe someone was making a cake.
It's entirely possible. Let's have a look then. So yes, mystery box number 4, flour,
Okay.
as well as that, sugar.
Yay!
So yes, we are allowed that in our van. Brings us on to our final mystery box.
I'm hungry now. I want a cake.
Box number 5. Another mix.
So, oh, this one. I think this is. So I think it was some more sugar, and then I think with it were some. I think this was some legal drugs.
So there's definitely sugar in there.
Yes.
Not illegal drugs though.
Oh no.
Explosives.
Oh, but it's still not allowed on the van, so it all worked out in the end.
Yeah, you would have been half right.
I hope you did better than me at home, anyway.
Yes, hope you did better at home. So in reality, if there was to be a Terahertz security scanner, we wouldn't have people like myself and Jack and you all at home trying to figure out what was inside the packaging. You'd have some kind of computer which, when it scans the item, would have a big list of all things that it knows and be able to tell whether that can or can't be in the lab, in the delivery van. So now we're going to briefly move on to what we actually do in the lab on a day-to-day. As we quickly shift camera positions.
Okay, so here at Leeds, we are part of the Hyper Terahertz program, which Tom briefly mentioned before. And this is a group of universities that are working together to create better terahertz technology. These universities are University of Leeds, where we are, Lancaster, Cambridge, and University College London. What we're doing here at Leeds specifically is trying to make lots of high-power, stable terahertz lasers. And these can be used for all kinds of things. These lasers, these specific ones, are called quantum cascade lasers, or QCLs for short. And a couple of the professors in our research team are actually some of the people who first made some work with terahertz. These are like really tiny lasers, like smaller than a thumbnail. So QCLs they work using quantum mechanics, which is like crazy science. And they're made right here in our very own high-tech nanofabrication laboratory.
Just below our feet.
One key area we're trying to improve with QCLs is the temperature they work at. At the moment, they need to be cooled to below -100 degrees Celsius, even lower to work better.
Very cold.
It is very cold.
Very, very cold. As well as this, we have been working with space agencies to put these lasers on low orbit satellites, where we're looking at detecting atmospheric gases to help investigate climate change. And as well as this, we're looking at putting them on some other satellites going far out into deep space and looking at gases out there as well. But for a bit more of a terrestrial application, we've also used QCLs to develop high precision imaging systems. Some examples here just on the presentation. We'll be using them to detect things like drugs, knives, and as well as something less security based, looking at cancer tissue as well. So yeah, we had a lot of these drugs and explosives supplied to us by the UK government to test and try and figure out if we could image them and figure out what was what. As well as using these QCLs, we also have other techniques of making terahertz light. The coolest of which is we get a really, really powerful laser. You focus it to a really, really small spot, and you basically end up ripping apart the air and creating a ball of plasma.
That sounds amazing.
It's really cool. We were hoping to show you a little tour video of the lab, but due to COVID restrictions and things, we were unable to film this. But any questions that you do have about the what it's actually like to be in the lab and working with as a scientist, we're more than happy to answer very shortly. I hope you found this session interesting. If you'd like to find out a bit more about terahertz science, some of our colleagues on Hyper Terahertz will be presenting on Monday the 12th of July between 8 and 9 p.m. We have Eleanor Nuttall here from Leeds, Lucy Hell from UCL, and Nikita Alman from the University of Cambridge. I think that about wraps it up for us. I'm sure you've all been a lovely audience at home. I think we've got enough time left for any questions you'd like to ask us now.
And don't forget to check out all the other amazing events going on across the Be Curious Festival as well.
Oh, thanks guys for the great plugs on our other events. Yeah, get booked on grown-ups get booked onto that Be Curious Lates next Monday. Thanks Thomas, Jack and Nick for a whistle-stop tour of your sort of terahertz technology and how it can identify all those things, good and bad.
Yes.
So guys, in the questions, please pop your questions in the chat. What is it like to be a scientist and things like that? And how do they work in the lab? And I've spotted one from Kieran already that I noticed this too. So the guy in your picture in the lab, he had some like dark sunglasses on. Is that what do you have to wear them in the lab?
Yes. So it depends on what lasers you work with. The ones Jack works with, I don't think you need laser goggles.
No, mine are fine. Mine are safe.
But I work with a really big, powerful laser, so we have to have these huge. Imagine like ski goggles, but they're sort of tinted green, and they're done in such a way that blocks out all of the really intense red light that our laser generates. We also have a different coloured goggles, some orange ones for when we're working on a different part of the laser, where you've got a really intense green laser and a really intense red one at the same time, and you can barely see anything at all when you put them on.
They're like safety goggles.
Yeah.
But
safe. They sound a bit dangerous if you can't see anything with them on.
Yeah.
So it sounds like to me these lasers are, I mean, they're obviously so powerful, like you showed us. So could they damage your eyesight if you didn't wear these safety goggles while you were working with them?
So the QCLs are completely safe because they don't interact with your eyes. But the other lasers we use to generate things like the plasma, they're really powerful. You're not allowed to wear watches or anything like that in the lab, in case you put your hand in the beam, you get a reflection into your eyes. It'd make them go pop like a balloon.
That sounds pretty horrible and not what we want to happen to our researchers at the University of Leeds. I've done a walk around the School of Engineering before and seen all sorts of like hazard suits and everything that you have to put on. And they have, is it called like a wet room, like in case you get chemicals on you in some of the bits?
Yeah. So in the basement bit where they fabricate the QCLs, they have to have a lot of that protective equipment on. We don't need that in the lab itself. But
yeah, in the clean room I work in, there's like a full body suit to stop like any skin cells getting on any of the equipment you're using or any hairs falling off, and that the air is also like pressurized, so there's fewer than like I think it's 100 dust particles per square meter or something in the air to keep everything really clean.
Yeah, because the devices you're working with are so small that even the smallest piece of hair on your sample can completely ruin it. Yeah.
Wow, gosh, I wouldn't like to be in charge of cleaning your lab.
Yeah. And then as well as that, speaking of dangerous things we work a lot with liquid nitrogen and liquid helium. So these huge canisters of compressed gas, compress enough that it becomes liquid. So liquid nitrogen is about, I don't work in Celsius anymore.
Minus 200.
Yeah, minus 200, and liquid helium is minus 290. It's 4 degrees above absolute zero, whatever that is in Celsius.
Yeah, and we need these, like we said, to cool down the QCLs because otherwise, if they're close to room temperature, they just don't work.
Yeah.
Wow, okay, really, really cold. I've got a question here from Jem. Oh, actually, it's been asked by CC and R. What happens to the lasers when they go out to space?
Nick, you're probably the best one to answer about this. You work with that.
I think you're better to explain. You're working like heterodyne.
Okay, so the way they work is
It's hard to explain this.
It is a bit hard to explain, but basically, we don't point the laser at the gas for it to work. There's a different detector which detects all sorts of light. We then shine our laser onto part of the detector, which makes it only detect that part of the light spectrum.
It's worth pointing out as well that these lasers work a lot better in space. Most light, especially the light that we work with, can only go a very short distance in the air because it gets absorbed by the water in the air.
Yeah.
But in space, we don't have that atmosphere, so it can go much, much further, and we can do much more with it in space than we can do here on Earth.
Yeah.
Wow, so loads of potential for this technology to help us explore much further afield into the galaxy.
Yeah.
Super amazing. So thank you so much, you guys, Thomas, Jack, and Nick behind the scenes. Although Nick did cause that little technical blip, I'm going to say. Did he? Did you trip over a wire, Nick?
That was me. That's my bad.
Sorry, Nick. Okay. Thank you guys so much for a fascinating session. I'm going to wave you goodbye. If everybody can say goodbye to those guys in the chat and say a big thank you and let us know how you enjoyed the session, that'd be brilliant. Thanks, guys. So we've had some incredible contributions and comments in the chat today. And I'm going to take that little cue from CC and R's question about space. If you guys watching at home love space, you have to join us this Saturday. We are going on a super trip into space, and we've assembled a crew of space scientists, Antarctic explorers, people who work on the satellites to look at, watch the Earth from space, oceanographers, and they are there to be grilled. They want your questions. They're going to show you some hands-on activities, and they sort of want to take you on that journey into space with them. We might even meet somebody who works with astronauts along the way. So tune in for that one on Saturday. And you can see that event and lots more. We've got still loads more to come later this week and next week in our programme at www.leeds.ac.uk/be curious. So we had a brilliant afternoon there learning about these powerful lasers, how we can use them to detect things good and bad. And I think you enjoyed it in the chat, but I'd really like you to tell us if you did. So you can drop that in the chat. But also, and maybe this is one for the grown-ups watching, if you enjoyed it, can you let us know using our evaluation form? We have dropped a link in our chat. Yes, we have. So you should be able to click that there. And it's just here below, but that's a bit of a funny one to sit and type out. So you might want to click that link in the chat. Grown-ups, if you signed up via Eventbrite, you will receive an email tomorrow with a link to that as well. So if you've not got time to do it right now because you're heading off to cook tea or do other things, you can do that a little bit later when it suits you. Thank you so much for everybody for getting involved today. Thank you to Merrin and Phoebe who've been chatting to you on the chat, our moderators today. And yep, don't forget to look at the rest of the Be Curious programme. That's it from us for this afternoon. And hopefully we'll see you again very soon for more Be Curious fun. Goodbye from us.